All right, so today we're going to do some solving exponential and logarithmic equations. So we're going to really combine a lot of the things that we've learned so far in this chapter and throw it all together in one to solve a bunch of different problems. Here we go. So we're going to combine the concepts of exponential functions and logarithms today to solve equations involving a mixture of the two. We're going to look at strategies for solving exponential equations, strategies for solving logarithmic equations, and then several sample questions we'll work on together, and then of course some practice. It's not going to seem like a huge amount of new material today, but it is still going to be really important because there's going to be some new tips and strategies that'll help you with more advanced questions than we've seen before. Here we go, let's go. So, solving exponential equations, I want you to recall that we initially learned that in order to solve an exponential equation, you need to ensure both sides of the equation are expressed as powers with the same base. That's still, of course, a very viable strategy. That is something that will be the most useful strategy for most cases that you'll look at. But again, it isn't the only case, but let's make sure we know how to do it. So first things first, I'll do the one here on the left here. 27 to the power of x minus 4 equals 3 times 81 to the power of 2x. Well, just right off the bat, you kind of have to look at all the numbers that are in there and say, okay, what's a common power that we could have, like common to all those pieces? So what could be a good base that we could have? Well, I can tell you right now, 3 would be a good base because I know 27 is 3 to the power of 3 and 81 is 3 to the power of 4. So I'll rewrite this. I'll say this is 3 to the power of 3 to the power of x minus 4, which equals 3 times 3 to the power of 4 to the power of 2x. Now, the next thing I'll do is, of course, because on this one we have a power, we can just multiply those powers together. This would give us 3 to the power of 3x minus 12. And on this side, we'll leave this 3 on the outside, and then 3 to the power of 4 to the power of 2x would be times 3 to the power of 8x. Now, here's what's interesting on the right-hand side. Because we have 3 times 3 to the power of 8x, you can think of this 3 on the outside as 3 to the power of 1. When you multiply two powers with the same base, you add the exponents. So this gives us 3 to the power of 3x minus 12 equals 3 to the power of 8x plus 1. So that's where this 1 is going. You're adding it on to this one because you're multiplying powers with the same base. Now that they have the same base and just the exponents are different, you can ignore the bases altogether and just solve the remaining exponents. So 3x minus 12 equals 8x plus 1. And then, of course, we can bring all of our x's to one side, and I'll minus this 1 to the other side. So we have negative 13 equals 8x minus 3x is 5x. And then, of course, that's going to leave us with x equals negative 13 over 5. And leaving it as a fraction is good enough. You could put it as a decimal if you wanted to. That'd be like negative 2.6, I think. But a fraction is just fine. All right, we're going to do the next question here. Once again, let's try to find a common base between these two things, 216 and 1 over 36. Well, this 1 over 36 is kind of my hint that this might actually have a base of 6 instead. And if you try 6 to the power of something, you'll find 6 to the power of 3 is actually 216. So we'll rewrite this now, 6 to the power of 3 to the power of 3x plus 2 equals, now this is the one that's a little bit weird as well, because it really should be 1 over 6 squared. But 1 over 6 squared is a reciprocal of, 6 squared. So you might as well just make this 6 to the power of negative 2, because a negative exponent just takes a reciprocal and then puts that power on the denominator. And then, of course, that whole thing is to the power of x minus 3. Once again, do the power of a power rule here. You're going to find that 6 to the power of 3 times 3x is 9x. 3 times 2 is 6, so 9x plus 6. Equals 6 to the power of negative 2 times x is negative 2x. Negative 2 times minus 3 is plus 6. All right, so now they have the exact same denominator. We might as well just, the exact same base. Well, let's now just ignore those bases and solve for what's remaining in the exponents. So 9x plus 6 equals negative 2x plus 6. I would add 2x to both sides, and that'll give us 11x. Now minus 6, so 11x equals 0. That actually means when you divide by 11 on both sides, you'll see that x is equal to 0, which is kind of an unusual answer. We don't really see that too often. But in this case, it definitely did work. The answer to x, the solution to x in this case, is 0, and there's nothing wrong with that. It still is a number. It's still a number that you could throw in there for the value of x. All right, so the next one. You can convert an exponential equation into a logarithm to solve it sometimes as well. So in other words, using that whole strategy saying, oh, get both sides to have the same base, and it doesn't always work. Like in this very first one here, 6 to the power of x equals 41. You can't write 41 as a base of 6, so you don't really have any choice here. You have to use logarithms. We've kind of seen this before as well, so let's just switch these around now. So 6 to the power of something equals 41. Start with your base. That's going to be the base of your log. So we're looking at a log of base 6. And the thing that goes in the log is the answer to the exponential function, so 41. And that's going to equal the exponent, which is x. So x is going to equal log base 6 of 41, but that's not a real solution. We need to actually solve that. You could use that strategy that I taught you that last day when we learned about the laws of logarithms, right? And that basically would say that x is going to equal log of 41, and that's just a normal log, right? So log base 10 of 41 divided by log base 10 of 6. If you throw that in your calculator, you're going to find, I'll just do it to the nearest hundredth here, you're going to find that x is equal to 2.07. So we found the solution by changing it into a logarithm. And again, you would never have found 2.07 being the value of x, leaving it as an exponential function. So that's where logarithms come in. It helps us solve for those unknown exponents. All right, next one. 3 times 4 to the power x minus 1 equals 15. If you want to try this one on your own, you're more than welcome to, just by the way. I know I might not always mention it in the videos, but if you ever want to give these a shot on your own, just to see if you really understand it, go for it. Now, I'm going to go over this one, though. We don't like it when there's a coefficient out in front, right? So we really should try to rearrange this however possible, and I think the best way to do it in this case is just to divide by 3 on both sides first. So that's going to give us 4 to the power of x minus 1 equals 15 divided by 3, which is 5. Now, obviously, there's no way to get 5 as a base of 4 as like a power. So there's no way we're going to do it that way. We have to use logs. So we're going to say log base 4 of 5 equals the old exponent, which is x minus 1. Now, once again, we can actually calculate log base 4 of 5, kind of using the same trick we did over here. So you can just go log 5 divided by log 4. And log 5 divided by log 4 is actually going to equal 1.16. So 1.16 equals x minus 1. And of course, we still need to solve for x, so let's add 1 on both sides. You're going to find that x is equal to 2.16. And if you're ever not sure if these answers work or not, you can always plug them back into the original question and see if it more or less is correct. Now keep in mind, these were just rounding approximations. So when you do throw them back in to the actual equation, it's going to be pretty darn close, but not perfect. And that's okay. Almost always when we do questions like this, especially when you're evaluating logs, you are going to get like an irrational decimal number. Just standard practice is to round to the nearest hundredth. It just keeps things cleaner than usual. All right, now for the really weird ones. Other times, especially when a power equals another power, like in these questions, we have a power equal to another power, and there's no way to get those bases to be the same. You have a really weird strategy that comes into play, and this is new. We haven't seen this one yet. The new strategy is literally take the log of both sides. This can be really weird, like it can really throw a lot of people off, but bear with me here for a moment. It'll actually make your life a lot easier in the long run. So we'll start with this one on the left. I'll show you what I mean. You probably are not going to want to try this one on your own first. You'll want to see how I do it. Whatever you do to the left side, you can also do the right. Taking the log is one of those things. So we can say log, and just the normal log base 10 of 17 to the power of 2x minus 3 is going to equal log of 3 to the power of x plus 2. All I did was took the log of both sides. If this thing equals this thing, then logically the log of that thing equals the log of that thing as well, because they were the same thing, right? So it should work. Now that I've done this, hopefully from the laws of logarithms we learned last day, you can remember when you take a log of something that has an exponent, the exponent can actually drop out as a coefficient out in front. In other words, if you wanted to see this in action, this 2x minus 3 is going to come out in front, so 2x minus 3, and I'll leave it in brackets because it's the whole thing, times by log of 17, which is just what's left over in there. And then the same thing can happen on this one. This exponent needs to come down, so it's going to be x plus 2 times by log of 3. All right, so here's where things get really messy. Now, because of these brackets, of course, this log 3 would have to bounce through all this, and this log 17 would have to bounce through this as well. So it kind of gets to be a bit of a mess. And you have some flexibility and freedom on how to do this. And really, I don't have much rhyme or reason to how I go about it. But basically, I like collecting all of my logs on one side. Now, this log here, this log 3, is multiplying this x plus 2. So I can actually divide both sides. I'll even, like, I know I don't usually do this, like I don't usually show all the steps, but I'll do it just to make things more clear. I'm going to divide both sides here by log of 3. And that's going to knock this one out. And of course, what I do to the right side, I have to do to the left side as well. I'll just hit this piece because, again, with multiplication, you could divide the whole thing, but you might as well just divide one piece here because it's all the same. I'll divide this by log of 3. Now what that's going to do is it's going to free up our x plus 2 on the right-hand side, but it's also going to turn this log 17 divided by log 3 into some really weird number. And I'm actually going to calculate that number right off the bat here because, again, in log form, it's not really clear what that is. So just follow along with me here for a second. I'm going to leave this 2x minus 3 alone. But in my calculator, I'm actually going to calculate log 17 divided by log 3. And when I do that, I get about 2.58. So 2x minus 3 times log 17 divided by log 3, which is 2.58, is going to equal the remaining x plus 2 on this side. Now that we have this as a decimal here, it hopefully is a little bit more clear what we would have to do next. Because of these brackets, this 2.58 needs to double dip through it. So what we're going to get is we're going to get 2 times 2.58 is 5.16x minus 3 times 2.58 is 7.74, and that equals x plus 2. Now let's gather all of our x's to one side and we'll move the number to the other. So if I minus x on both sides, you're going to have 4.16x, because remember this is technically just 1x. So minus 1x here gives us 4.16x. I'll add this 7.74 to the other side. That's going to give us 9.74. So 4.16x equals 9.74. Look how weird this got so quick. But anyway, x is going to equal 9.74 divided by 4.16, which is 2.34. So wow, that was a really, really, really weird one, but those aren't rare. They do come around quite often. We'll do another one here, just to make sure we really drive this home. Hopefully this one will make a little bit more sense. 2 times 3 to the power of x equals 11 to the power of x minus 2. Once again, there's no way to get these two sides to have the same base, so we have to use that weird strategy where we just take the log of both sides. So log of 2 times 3 to the power of x equals log of 11 to the power of x minus 2. I guess the next thing we would have to do, like usually we'd bring the exponent down, but notice this is something times something else. The 2 times a 3 to the power of x. Let's break this apart because we actually had a log law that said if you are multiplying two things inside of a log, you can break it apart into an addition. So this is going to become log 2 plus log 3 to the power of x equals log 11 to the power of x minus 2. Now we can use that exponent rule where we drop that exponent down in front of them. So we'll say this is log 2 plus x log 3 equals x minus 2, and again in brackets because it was a binomial, it's the whole thing coming down, times by log 11. I guess the next thing we would have to do here is we should really turn all of these logs into actual numbers here, just so we can really see what's going on. Well, log 2, if you put log 2 in your calculator, and again, this is log base 10 of 2, so you literally can just go log 2 in your calculator, you're going to get about 0.30, plus, if you do log 3 in your calculator, you're going to get 0.48, but notice there's an x attached to it, so we'll say it's 0.48x equals x minus 2 times log 11, and log 11 is 1.04. This 1.04 needs to double dip through these brackets here, so we're going to have 0.30 plus 0.48x equals 1.04x minus 2 times 1.04 is 2.08. And then we got to bring all of our x's all to one side, so I'll move these x's over, and then I'll move this 2.08 over to the other side, so we'll have 2.48 equals, and minusing this x over to the other side gives us 0.56x, and then divide by 0.56 to get x by itself, so x is going to equal 4.43. And again, I just kept everything to the nearest hundredth just to keep things simple. Although there was nothing simple about that. That was quite a tough question. So again, just watch these ones. If you ever have a power on both sides of an exponential function, you've got to take the log of both sides. And I know it's a pain. You can clearly see how much work it is, but break it down one step at a time. And don't be afraid to turn a logarithm into a decimal. There's nothing wrong with that. If you have something like log 2 or log 3 or log 11, turn it into a decimal. It makes things a little bit more clear. Even back in this question, in this step I did right here, alternatively, I could have turned log 17 into a decimal and log 3 into a decimal, and maybe that would have made things easier, just looking back. Whatever floats your boat, give them a try. All right, now we're going to move away from exponential functions, sort of. Again, these are all interconnected. We're going to move towards solving logarithmic equations. Now, when solving logarithmic equations, it's generally easiest to simplify each side as much as possible using the laws of logarithms. In other words, try to get it as like a single log on both sides. Now, if there is a single log on each side of the equation with the same base, you can actually ignore the logs and just solve the leftovers. So if you have like log of 4 or log base 4 of something equals log base 4 of something, you can just ignore the log base 4 and just solve those somethings, the leftovers that are inside. Now, one other thing, and you guys are going to hate me for this, but this is just how logarithmic equations work. When you answer a logarithmic equation, so if I start with a bunch of logs, you actually always have to check for extraneous roots. And yeah, like I know it sucks. It's really, really annoying. But again, logarithms are kind of a finicky thing, and they can actually produce some issues. It's not very often that they do, but just take your final answer you get, plug it back into the original thing and see if it more or less worked. That's all we're asking for here. That's all you got to do. All right, we're going to start with the very first example here. Log 3 plus log x equals log 2. So again, try to get it so it's one log on both sides. Well, log 3 plus log x, from our log laws, that means we can just multiply these two things. So really we have log of 3 times x equals log of 2. Okay, so now, of course, since it's log of something equals log of something, and they have the same base in the log, it's log base 10, you can just ignore the logs altogether and just say it's 3x equals 2. It's kind of like what we just did, except it's working backwards. Remember, we were able to take the log of both sides? Well, you can also get rid of the log on both sides if that's all there is. Okay? Remember, if it was like log 3x equals log 2, and then you had like plus 17 over here, well, then you wouldn't be able to do it because it's not just a single log on each side. Anyway, I'll stop rambling. Let's just divide by 3 on both sides. We have 2/3 is x. Now, of course, we should always test this. You have to look for extraneous roots, and to do that, it's just a quick verify. I'm not going to be picky with what I'm looking for a verify here. You don't have to show like literally all your work. I'm just looking for either a check mark or an x. I'll show you with all the work for this time, but from here on, I'll just give you a check mark or an x. So to verify, I can go log 3 plus log of x, and x we found was 2/3. And I want to see if that's equal to log 2. If you plug this in your calculator, and you plug this in your calculator, you're going to see that this side equals this side. So for a verify, just give it a check mark. That's all I need to see just to make sure that you've done it. Now, of course, if you say verify and a check mark and it didn't actually work, I'll know it didn't work, right? So in other words, you're not going to get full marks. But you do need to verify just in case it didn't. In this case, take my word for it, it's going to work. No worries. All right, next one. Log base 4 of x plus 3 minus log base 4 of x equals log base 4 of 7. So this one looks a lot more intense than the other one, but really it's not a huge amount more. Once again, get a single log on both sides. Notice on the left side here, we have a log minus a log. That just means you need to divide what's inside each of these logs. So this is going to write as log base 4 of x plus 3 divided by x, and that equals log base 4 of 7, as we started with. Now notice you have a single log equals a single log. Just ignore those altogether. And you can say that x plus 3 over x equals 7. Now we need to solve for x. So I think the easiest way of doing this is probably to multiply by x on both sides. So we have x plus 3 equals 7x minus x. Now we have 3 equals 6x. Divide by 6, and you're going to find that x is equal, you write it as 1/2. I'm actually going to write it as a decimal here. X is 0.5. Now, as always, because we started with a bunch of logs, we need to verify. Okay, so to verify, I'm not going to show all the work. You just plug 0.5 in here. So do log base 4 of 3.5 minus log base 4 of 0.5 and see if that's equal to log base 4 of 7. As a matter of fact, you actually could even do this algebraically. You wouldn't actually need a calculator for this. You could use your log laws and actually confirm it, but we can actually verify, yes, this one did work. I know I'm not really selling the point, you always got to check these too well right now because everyone we've looked at so far has worked, but believe me, you got to check these every single time. All right, now, other times, you need to get a single logarithm on one side and then a constant on the other side. In these cases, it's usually easiest to change to an exponential function and then solve. So these are the cases where you'll actually start converting back to an exponential function. Now, just as before, when you're starting with a logarithmic equation, if you're starting with a log, you always need to check for extraneous roots here. So again, if you're starting with logs, you need to check for extraneous roots. If you're starting with an exponential and then turn it to a log, you don't have to worry about it. But if you started with a log, you need to check for extraneous roots. All right, anyway, we've only got a couple more questions. We're actually almost done. We've made decent time today. So solve for x on this one, log base 4 of x plus 2 plus log base 4 of x minus 4 equals 2. Okay, so first things first, it's always nice to simplify it to get a single log. We have logs on the left side, we have no logs on the right side, so we're kind of out of luck on that one, but let's not worry about that right side. It's literally just a 2. You don't have to worry about it. It's literally just 2. Calm down. Let's combine these two to make it a single log. To make this a single log, of course, since we're adding two separate logs together, you got to multiply what's in there. All right, here we go. Log base 4 of x plus 2 times x minus 4. Interesting. So in other words, we're going to have like a quad, hold on, why on earth is the word not coming to me? A quadratic, thank you. A quadratic that's not going to be, very obvious in this is what I'm trying to get at here. Anyway, so that's what we got as a single log. This is going to equal 2. Now, I guess maybe what we could do is now remove our log. Because right off the bat, you can say, okay, log base 4 of this equals 2. What the heck? How on earth are we going to find x? Well, we need to turn to an exponential function. Start with your base. Base is 4. The exponent's going to be the answer, so 2. And the stuff that was in the log is the new answer to the exponential function, so x plus 2 times x minus 4. 4 squared is just 16, so we can say 16 equals this times this. We're going to have to expand this out because, again, you can only solve a factored quadratic if the other side was equal to 0. And of course, just minusing 16 here is not going to do any good, so we have to expand this out anyway. So use FOIL to expand this out. X times x is x squared. X times minus 4 is minus 4x. Plus 2 times x is plus 2x. And then plus 2 times minus 4 is minus 8. Now I'll bring the 16 over to the other side by subtracting it, and then I'll also combine my like terms here. 0 equals x squared. Negative 4x plus 2x is minus 2x. Minus 8 minus another 16 is minus 24. Okay, so now we have a new quadratic, x squared minus 2x minus 24 equals 0. To solve this, hopefully you remember, it's just a quadratic function. You can just use any of our quadratic solving tools. Personally, I'm going to try using my classic old sum product rule. So I'm looking for two numbers with a sum of -2 and a product of -24. Well, just thinking about two numbers real quick that would do that, I think -6 and +4 would make that work. Because -6 plus 4 is -2, and -6 times 4 is -24. Bingo, we got it. And because it's just a single x squared, just like a 1x squared right here, we can just like immediately snap to those two numbers. We can say it's x minus 6 times x plus 4 equals 0. And there we go. Where's this times this going to equal 0? Well, it's only going to equal 0 if this piece is 0, so x is 6. Or if this piece is 0, x is -4. But remember, we always need to verify. We got to check for extraneous roots. One or both of these, or maybe none of these, are extraneous roots. We need to check. All right, here we go. So for a verify, I'm going to start by verifying x is equal to 6. So I can plug 6 into each of these. So we're really going to be looking for log base 4 of 8 plus log base 4 of 6 minus 4 is 2. And we want to see if that equals 2. I'll spare you the work here. Plug in your calculator. That one is going to work. So I can put a box around this and say, yeah, x equals 6. That's one of my solutions. Now let's verify x is -4. I bet you're already kind of putting together where this is going to go. So what we're going to be looking for here is log base 4 of -4 plus 2. Well, -4 plus 2 is -2. So really right here, we're doing log base 4 of -2 plus log base 4 of -4 minus 4 is -8. That might not mean anything to you right now, but hopefully you remember, I think it was actually from last week, you can't take the logarithm of a negative number. It literally just doesn't work. If you tried doing this, again, you'd have to go like log of -2 divided by log of 4. If you're going to do that like old weird thing, your calculator is going to tell you it's a non-real answer. So in other words, right here, we can just put an x and say it's an don't know how to spell extraneous root. We found one. Boom, good. Told you they show up every now and then. You got to be careful. So in other words, this x equals -4. Don't put a box around it. Matter of fact, you can just like slash through it and go like, yeah, no, it doesn't exist. Show that you found it. Show that you verified it didn't work, but don't list it as one of your answers. So the only answer here is x is equal to 6. All right, I think this is the last one we're going to do here now. Solve for x. If you want to try this one, please be my guest. Remember, we want to get a log on one side and a number on the other. So here's how I'm going to do it. I'm going to bring this chunky log right here over to the left side, and I'm going to add 1 to get that to the other side. So here's where we're going. Log base 2 of x squared minus 2 minus log base, yeah, minus, hold on, I was thinking like, do I have to divide? No, we're going to minus this over the other side. Sorry, log base 2 of 1/2 x plus 5, and that's going to equal positive 1, because again, I moved this over and I moved this over. Okay, just so you know what I did there. Now, since we're subtracting two logs, we can combine them into one. Of course, when you subtract logs with the same base, you just divide them. So this will be log base 2 of x squared minus 2 over 1/2 x plus 5, and that equals 1. Now that we have a single log equal to a single number, let's turn it into an exponential function. So 2 is our base, 1 is our exponent, and our answer to the exponential function is this, x squared minus 2 over 1/2 x plus 5. Now, hopefully you recognize 2 to the power 1 is just 2. So you know what? I'm going to erase that 1 there. It's just 2. We're good. Now, we want to solve for x. Probably the best way of doing that is to multiply this denominator on both sides so we can actually start working with this, because having the x in the denominator is just a pain. So I'm going to times both sides by 1/2 x plus 5. So that's going to get rid of it right here. And timesing 2 by 1/2 x plus 5 is going to give us x plus 10, because 2 times 1/2 x is x, and 2 times 5 is 10. X plus 10 equals x squared minus 2. This x squared here is going to cause us some trouble, so let's turn it into a proper quadratic by moving everything else to the other side. This is going to give us 0 equals x squared minus x, and then minus 2 minus 10 is minus 12. So we're looking for two numbers with a sum of -1 and a product of -12. Well, those two numbers are going to be -4 and +3. So we can say that 0 equals x minus 4 times x plus 3, which tells us that our solutions are going to be x equals 4 and x equals -3. But before we box these, let's make sure we actually test to see if they're going to work. So what you got to do, and I'm kind of running out of room here, I didn't really plan this out too well, but I'll do my verify up here in the corner. Let's verify x is equal to 4. If you plug x is equal to 4 back into this, you're going to get 4 squared, which is 16 minus 2, so log base 2 of 14 minus 1, and we want to see if that equals log base 2 of 1/2 times 4 is 2 plus 7, so 7 is what we're looking at there. Long story short, if you throw this in your calculator, again, I'll save us the trouble, throw it in your calculator with x being equal to 4, you're actually going to see this one works. So this one's good, we'll put a box around it. Now you might be looking at this and going, oh, x is -3, I bet this one's not going to work. Well, let's see. X is equal to -3. If you put -3 here, -3 squared is 9, so we're looking at 9 minus 2, so log base 2 of 7 minus 1. And we want to see if that equals log base 2 of 1/2 times -3, so that's -1.5. And then -1.5 plus 5 is 3.5. Well, you're actually going to find when you plug this into your calculator that the left side does equal the right side. So x equals -3 also works. Surprise, surprise. You know, you might have thought otherwise, right? Both of those are acceptable answers. So there are two solutions this time, and there's nothing wrong with that. You definitely can have two solutions here. Whew, okay, that was a lot to cover today. Hopefully you were able to grasp it all. We are done. So for practice, please do page 412, questions 2, 5, 7, 8, 10, and 11. I know that seems like quite a whole gamut of questions there, but again, this is really essential practice because it ties everything we've done all back together. Again, as always, if you have any questions, please let me know.